So we've defined a direct product of groups as being a group made up of ordered pairs, in which in the first element of the pair, the elements of one group get to have its own algebra, and in the other element of the pair, the elements of the other group get to have its own algebra, but we treat that ordered pair like a single element in the larger group called the direct product. In this video, we want to answer the question, if the groups that these elements came from were cyclic to begin with, then will that group that we get by forming the direct product also be a cyclic group? Under what circumstances is that guaranteed to happen? Let's come back to this picture from the end of our last video, when we looked at the direct product of Z mod 6, cyclic group order 6, with Z mod 2, cyclic group of order 2, that the identity element, 0, 0, in that direct product, can be thought of as all of the lattice points in the xy plane that inhabit the multiples of 6 in the x direction and multiples of 2 in the y direction. So all these purple points are identity elements in the direct product, Z6 product Z2. So if I take the element 1, 1 and I look at its powers, so if I add it to itself repeatedly, after I do so once, twice, 3 times, 4 times, 5 times, 6 times, I've now come back around to the identity element inside of this group. But on the other hand, if instead of Z6 product Z2, we had Z4 product Z3, now the sixth power of 1, 1 has not come back around to the identity, the purple points, inside of that product group. We need to go further. We need to go all the way up to 7, 8, 9, 10, 11, 12. So it takes me 12 iterations to get back to the identity when it's Z4 product Z3, compared to Z6 product Z2, where after only my 6th iteration I was already at the identity. But notice what else happens. At the 12th iteration I'm back to the identity again also. So the question is, when I have a product of two cyclic groups of order n and order m, what is the order of an element in that product? And then, under what circumstances is that direct product group a cyclic group? So as you might expect, the answers to those two questions are related one to another. First, we're going to talk about the order formula for an element. What's the order of an element in a direct product of two groups? And secondly, under what circumstances will that guarantee, this order formula guarantee, that the direct product of two cyclic groups is a cyclic group? So, how do we figure out the order of an element in any group is? Well, we just start raising it to some powers and figure out how many powers we have to raise it to before that element becomes the identity element in the group. But because in a direct product, the operation happens component-wise, the nth power of g comma h is going to be the nth power of g, taken as an element in the group capital G, comma the nth power of h, taken as an element using the operation of the group capital H. And so that is going to come back around to the identity as long as g has come back around to the identity, so we need enough powers of g to make g into the trivial element, but also we need simultaneously enough powers of h to make the nth power of h trivial as well. And because we need enough power to make g trivial, this exponent that we're using has to be not necessarily the same as the order of g, but it could be more. It just needs to be a multiple of the order of g. And then in the second component, in order to make h trivial, we need its exponent to be some multiple of the order of h as well. And the order of an element is the least such power that makes this happen. And so at the end of the day, if I need a multiple of the order of g powers to make the first component trivial, and a multiple of the order of h powers to make the second component trivial, and the order is the least such integer that accomplishes both, then that proves for us that the order of this element is going to be the least common multiple of the order of g and the order of h. We've seen a formula similar to this one before, back when we were talking about permutations. If I had a cycle that was disjoint from another cycle, then the order of their composition was the least common multiple of their orders. And that happened because disjoint cycles, because they're acting on disjoint sets of symbols, they're doing their own thing. They have their own algebra, similar exactly to how the elements in a direct product are doing their own thing with no interaction one with another. So their orders are the least common multiples for the same reason as the orders of disjoint cycles when we were talking about permutations. So what does this order formula tell us about when a direct product of two cyclic groups is a cyclic group? So let's come back to Z6 direct product Z2 and Z4 direct product Z3 once again. So our hunch was that Z6 product Z2 was not cyclic, Z4 product Z3 was cyclic. We actually proved that by finding a generator. So if I list out all the elements, all 12 elements in each of these two groups, the question I'm going to ask is, why shouldn't it have been a surprise that one of these groups was cyclic while the other one was not? So again, notice how Z6 sits as a subgroup inside of this direct product. It's the first row here. Z2 sits as a subgroup, which is the first column. Same thing over here. Z4, the first row, subgroup. Z3, first column, also a subgroup. The orders of elements are just given by the orders of the elements in each of these cyclic groups. 1s, 2s, 3s, and 6s over here, 1s, 2s, and 4s over there, and so forth. So if I take and I look at 1, 1, which was that element that we saw in a couple minutes ago, by the time we get to its 6th power, it comes back around to the identity. Well, that shouldn't be a surprise now, given the order formula, because the order of 0, 1 is 2, the order of 1, 0 is 6. Those are true because those are respectively the generators of Z2, which has order 2, and Z6, which has order 6, which are each cyclic by themselves. But the order of their sum, 1, 1, is going to be the least common multiple of 2 and 6, that is 6. And since that order is not equal to 12, this element doesn't generate the whole group. And indeed, if we continue, we find out that none of the elements in Z6 product Z2 can possibly generate the entire group, because every element's order is going to be the least common multiple of some divisor of 6 and some divisor of 2. But the largest such order that we can make is 6. So none of the elements in my group over here on the left are going to have order 12 and therefore generate the group. Therefore, we've proven now that Z6 product Z2 is not cyclic. On the other hand, in Z4 product Z3, when I take 1, 0, which generates the Z4 subgroup here on the first row, and 0, 1, which generates the Z3 subgroup on my first column, their orders, 4 and 3, combine via the least common multiple to produce an element 1, 1, which has order 12. But then that means that 1, 1 is our generator, because its order as an element is equal to the order of the whole group. So, there will be a generator for my direct product of cyclic groups, as long as there exists an element whose order as an element is equal to the order of the group. But the order of the group is going to be the product j times k. The order of our elements are the least common multiples of j and k. And so we're going to have a generator exactly when it's possible for those two to be equal. But it's only going to be possible for those two to be equal. The least common multiple of j and k, where here j is a generator of my z mod j, k is a generator of my z mod k, the orders thereof, that's what I mean. And the only time that the least common multiple of two integers is equal to the product is when those two integers share no common factors. In other words, when j and k are relatively prime. So this gives us a proof for the assertion that the external direct product zj product zk is a cyclic group if and only if j and k are relatively prime to one another. And so z4 product z3 is a cyclic group because 3 and 4 are relatively prime, but z6 product z2 was not a cyclic group because 2 and 6 were not relatively prime. And the stronger statement that we get for free out of this observation is that for those external direct products of cyclic groups which are cyclic, so in the case where the greatest common divisor of j and k is equal to 1, where j and k are relatively prime, in that case, because this direct product is cyclic and its order is equal to j times k, that's going to mean that this direct product is isomorphic to the cyclic group of order j times k. So when GCD of j and k is equal to 1, when j and k are relatively prime, this external direct product, zj product zk, is isomorphic to z mod jk. And that isomorphism sends any of the generators of this, for which we know now that 1, 1 will always be a generator in this case. It just sends that generator to the generator 1 of z mod j times k. This is actually a really, really valuable tool for us in classifying all of the finite abelian groups. What can they possibly look like? We now know that some building blocks, some cyclic building blocks, when I combine them together in a direct product, are going to give me a new group, a new kind of group which is no longer cyclic. But some building blocks, in particular, when their orders are relatively prime, when I combine them together using a direct product, I don't get some new kind of group. The result is again going to be cyclic, and its order is going to be the product of j and k. So for example, if my goal was to classify what are all of the finite abelian groups of order 12, and I ask myself, well, what about z4 product z3? What is that group exactly? well, that group is isomorphic to Z mod 12. So if my question is what groups of order 12 are out there that can be made in this way, the answer to that question depends on the different ways in which I can factor the number 12. I can factor it as itself, and therefore get the group Z mod 12, or I can factor it in these three other different ways. But we just found out that if I take Z3 and Z4 and I form a direct product, that direct product is isomorphic to Z mod 12, so I'm not getting any new group out of that. Similarly, Z6 and Z3 direct product Z2 would also be isomorphic to one another. And so the two groups that I would get from these factorizations of 12 here in the middle are not different from one another. But they're isomorphic, on the other hand, to Z6 direct product Z2. So what this actually proves for us is that the only finite abelian groups of order 12 are going to be isomorphic to Z mod 12, such as in this example, or are going to be isomorphic to Z6 direct product Z2. Those are the only finite abelian groups of order 12. The question about non-abelian is more intricate, and we can't answer it with our tools right now. But this gives us a really powerful way to classify, in this construction, what kinds of isomorphism classes of finite abelian groups can we make. When J and K are relatively prime, then when I take their direct product of those two cyclic groups, the result is going to be another cyclic group. When they're not relatively prime, then their direct product is not going to be a cyclic group, and so therefore it's going to be different from any group which is cyclic.